small electric aircraft, it's not only important to maintain good flight performance, but also to consider flight efficiency, especially since the battery energy storage isn't very strong yet. The detailed airfoil selection work isn't finished. In the previous video, I kept the GA30U315 wing, so I'll use that as a reference and add LS0413 and NACA2301 3.5 for comparison. First, let me explain why I chose these three airfoils. All three of them have good stall protection characteristics. The GA, being relatively thick, might lead to higher power consumption during cruise. So, I selected two slightly thinner airfoils for comparison. My goal is to find the one that offers the best balance between aerodynamic performance and drag. Before showing the results, I'd like to first share how I validated the reliability of my calculations. First, the CP comparison. Before comparing the aerodynamic performance data, I compared my simulation results with available wind tunnel data for the CP distribution. Unfortunately, I was only able to find CP data for the LS0413 airfoil. But since all three airfoils were simulated under the same conditions, I assume the validation results are comparable among them. The data I used comes from NASA Technical Paper 1498, where the CP distribution of LS at an angle of attack of 12 degrees is shown in Figure 13. There wasn't any tabulated data available, and I really wished GPT could help me extract those points automatically. But in the end, I went with the most traditional way: manual data extraction. After importing the data, we can see that the simulated results for both the upper and lower surfaces match the wind tunnel data quite well. In the wind tunnel test, the Reynolds number was 2 times 10 to the power of 6. Considering standard atmospheric pressure and reference air density, I used a flow velocity of 29.2 meters per second per unit chord length in my simulation, which is also within the expected speed range of my small aircraft. Validation of the turbulence model and mesh setup. I used the wall Y plus value to verify the accuracy of my turbulence model. The simulation environment uses a SST-K omega hybrid turbulence model combined with the gamma R E theta transition prediction method. To simulate the flow correctly in this environment, the model needs to be surrounded by a mesh, basically a finite element grid. It's important that the mesh can accurately capture the laminar, transition, and turbulent regions within the boundary layer. By checking the wall Y plus value, I can judge whether the first layer of cells near the wall is properly resolved, and whether the overall mesh gives a reasonable prediction of the flow field. A smaller Y plus value means that the first mesh layer lies inside the viscous sublayer, usually within a fraction of a millimeter from the airfoil surface. This allows the simulation to capture the true skin friction and the accurate transition between laminar and turbulent flow. In my setup, about 90% of all Y plus values are kept below 2, and the maximum Y plus is around 5. This indicates that my mesh and simulation settings can capture most of the fine details of the boundary layer very well, meaning the model is reasonably accurate and reliable. Observation of the surface. Friction coefficient, CF. At the airfoil surface, the flow velocity is 0 and gradually increases with distance from the wall. This represents the strength of the surface friction. The coefficient CF is the dimensionless value describing this effect. Generally, CF is the highest near the leading edge of the airfoil, where the flow accelerates rapidly and the velocity gradient is steep, meaning stronger surface friction and higher turbulence energy. Toward the midsection, CF gradually decreases as the velocity gradient becomes smoother. When the angle of attack increases, the surface flow may separate, forming turbulence or even reverse flow. In those regions, CF approaches zero. By observing the variation of CF, we can understand the velocity gradient along the wall surface. A larger CF means a steeper velocity gradient, while a CF close to zero indicates either a nearly uniform laminar flow or a turbulent region with almost no velocity gradient. By combining the analysis of Y plus and CF, we can assess the accuracy and validity of the simulation model. This allows us to clearly visualize the flow details and quantify aerodynamic losses more precisely. After completing the extensive computational evaluations, let's take a look at the performance of the three airfoils. This time, I set the angle of attack range from -7 degrees to 20 degrees, and the velocity range from 20 meters per second to 50 meters per second. My goal was not only to compare the stall characteristics at different speeds, but also to examine their cruising performance under varying conditions. 1. Let's start with the most straightforward parameters, the lift coefficient, CL, and drag coefficient, CD. For assessing stability, the CD results remain consistently steady, reaching a minimum around zero angle of attack and forming an overall flat parabolic trend. As for CL, I used the same averaging method as in the previous video and compared results across all speeds. The GA shows the highest peak CL at a 15-degree angle of attack among the three, and its post-peak decline is relatively gentle, giving more margin for recovery after stall. Finally, I compared the CL/CD ratio to observe the width and steepness around the peak, which reflects the aerodynamic efficiency. 2. Stability evaluation. Pitching moment, CM. When CL equals 0, CM0 is positive. This means that under zero lift, the pitching moment about the quarter chord, 1/4 C, is positive, i.e., the main wing produces a nose-up moment. To maintain equilibrium, the tail must provide a nose-down moment. For the NACA airfoil, the minimum CM0 is 0.007. Meanwhile, a negative slope indicates static stability, as I explained in my earlier video on stability. When the angle of attack exceeds 0 degrees, both the GA and NACA airfoils show a slightly weaker static stability at higher speeds. 3. Cruise efficiency comparison. The method I used is based on the constraint of lift equals weight. At different speeds, I first determined the required CL values under this condition, then found the corresponding angle of attack to obtain the CL/CD and CD results for that angle. By comparing the three airfoils, we can see that under the same lift constraint across all tested speeds, the GA airfoil shows the lowest CD and the highest CL/CD ratio. This means that GA delivers the best cruise efficiency among the three. So, which airfoil should we choose? Not yet. I don't have a final answer. All of the above calculations assume an ideal surface that's relatively smooth. But what if the airfoil surface becomes rough due to aging, bug splats, dust and sand, or even icing? Next, I'll rerun the computations while accounting for these real in-flight conditions that are highly likely to occur. Thank you for watching, and I'd really appreciate any of your feedback and suggestions. See you in the next video.